Good morning, dear students. I'm audible. Good morning, dear students.
Good morning, sir.
Okay, welcome to image processing class. So we are discussing on module 5, isn't it? So we are making some discussions on image compression. So under this image compression, so we have already made some discussions on coding, in particularly arithmetic coding. We have completed that. So today we are going to discuss on interpixel redundancy. Okay. I'm going to share this slide. I'm going to explain this. Later on that we are going to solve a problem on this. Students, can you see this slide? PPT ಕಾಣಿಸ್ತಾ ಇದೆಯಾ?
Yes, sir.
Okay, that is interpixel redundancy. Okay, interpixel redundancy. So what is this interpixel redundancy? How it is introduced in image compression and all those things we are going to study here. So now, so data and information. ಕಾಣಿಸ್ತಾ ಇದೆಯಾ PPT? Data and information. PPT ಕಾಣಿಸ್ತಾ ಇದೆಯಾ? Data and information ಅಂತ.
Yes, sir.
Fine, very good. So now, so what is data? So data is not something as information. Idar munchene helite nanu already I have explained. But once again, image compression, whenever we are going to discuss, the concept of information can be conveyed through the data. This will be always discussed, okay? Now the data, it is the means with which information is expressed. I want to express some information. How this can be achieved? How this can be done? This can be done via the data. That is, the amount of data can be much larger than the amount of information. See, the basic, the difference between data and information is the amount of the data is always higher than the amount of information, because information contains something to be conveyed, whereas data is always considered in terms of measuring, in terms of storage. So that is data that provide no relevant information. Suppose you have some data. If the data does not provide any kind of information for you, so these type of data which never gives valuable information for you, so such type of data we can call them as redundant data or redundancy. That is duplicate data. A data which never gives valuable information will be considered as redundant data or redundancy. Next, image coding or compression has a goal to reduce the amount of data. So basic objective of image coding or compression is you try to reduce this redundancy, okay? So that whatever the data you have in your hand, that is always good, legitimate, and also it can provide valuable information. Suppose if you have data which never gives valuable information, it is wastage. So that is why try to reduce these type of redundant data. So that is the objective of image compression. So like we have N1 is equals to data, N2 is data minus redundancy, okay? Suppose if you have data and if you reduce, if you eliminate the redundant data, that is the data which is not valuable, whatever the residue, that is N2, that will be of good quality. That is N2 is compressed image. That is compressed ratio is equals to N1 by N2. N1 is a original data and N2 is a compressed data, whereas the redundant information has been eliminated. So now relative redundancy nu helidine nanu nimage ಎರಡು formulas ಮುಂಚೆನೇ ಹೇಳಿದ್ದೆ already. That is relative redundancy is equals to 1 minus 1 over CR, that is compression ratio. So we'll continue our discussion here. So different types of redundancy. ಯಾವ ತರ redundancy ಬರುತ್ತೆ? First one CR, that is coding redundancy. Arithmetic coding already ಹೇಳಿದ್ದೀನಿ ನಾನು. Run length encoding is also one of the concept which comes under interpixel redundancy, and we have PVR, psycho-visual redundancy. So what is the CR there? Some gray levels are more common than others. Means there are some gray levels which are more common. ತುಂಬಾ ಸಲ repeat ಆಗುತ್ತೆ than others. Others means other intensity images or other gray levels. IR stands for interpixel redundancy. That is what today's concept. Okay, interpixel redundancy. So the same gray level covers large axes or large areas. Means, for example, there may be a 255 gray level. So if you consider this entire image, 255 is present everywhere. So this is 255. This is also 255. This is also 255. This is also 255. Means interpixel redundancy means we can predict the neighboring pixels intensity level by using present pixel information. So this is so called as the interpixel redundancy. Next, PVR stands for psycho-visual redundancy. And there, the eye can only resolve 32 gray levels locally. Okay, so locally means neighboring pixels we can identify only up to 32 gray levels. Means if you just consider a pixel is a very micro, or we can say very minute concept, which is very we have to enhance this, we have to magnify this, the pixel, so that we can understand the depth of color. Okay, so already I have explained that in my in tool, if you go for RGB, the 3-layer, the three channels, how it has been divided. Suppose if you convert a color image into grayscale image, how the layers are, how a single layer will be always present. 0 represents black, 255 represents white, and all the in between will be considered as the shades. So among them, the neighboring 32 gray levels only we can identify. That is the persistence power of our eye. Okay, so more than 32 gray levels our eye cannot recognize. So these type of redundancy, there are 3 standard types. One is coding redundancy, interpixel redundancy, and psycho-visual redundancy. Now, today our discussion, we are going to focus on this interpixel redundancy. So this is the image compression model. Okay, how image compression can be done. So that is compression and as well as decompression. We can also call them as image compression model. So in image, careful observe, go through this. You have a original image. So this is the original image, and we are compressing this. We are making some compression. So we are applying a compression. The outcome, the result is a encoded file. So this is an encoded file. The amount of storage, the storage required for this encoded file will be always lesser than the original, because we have made the compression. So that is why we also call them as compact information anta kuda ನಾವು ಇದನ್ನ ಕರಿತೀವಿ. ಯಾಕೆ compact information means for storage or transmission, because always when you want to transmit a given file through the network, so there may be always issue related to bandwidth and the data rate. Okay, so that is why we have to keep in that in our mind, what is the bandwidth of the network channel or optical fibers, or it may be through the mobile networks. The bandwidth we have to always consider into for transmission. So that is why we have to compress the data. The compressed data will be taken as a compact information, and once it reaches the destination, see, it has been routed through the network. So once it reaches the destination, so it will be first, initially it will be compression, no? So now it will be decompressed. So once you decompress it, you can get back the original image. If you get back the original image, the mechanism is so called as lossless compression. If there is no loss of bits, the original image will be, we are going to get the same image as it is without any loss of bits. Then the mechanism is called as lossless compression. On the another hand, suppose if you, whatever the image what you have decompressed, so that image, if some information has been lost due to some network issues or maybe decompression algorithm problem like that, so then whatever the original file what we are going to retrieve, so that will be lossy image because some information has been lost over there. So this is so called as an approximation of the original image. It is not exact original image. It is approximation because it is closer to the original image. It is not a original image because some information has been lost due to maybe network issues, maybe algorithm issues like that. Okay, so this is so called as a image compression and decompression model. Yes, Arthaktidiya, dear students.
Yes, sir.
Shall we proceed?
Yes, sir.
Okay, so now we continue. Image compression. So image compression can be, so we have two types of, that is what already I have explained. One is lossless and second one is a lossy. So lossless is also called as a reversible. Reversible means the original image, whatever we have compressed, it can be, we can get back the same original image. So that is called as a reversible. On the other hand, non-reversible means whatever the obtained decompressed image, it is not exact as original image. So in reversible, so with no loss of information, so exact image will be retrieved. A new image is identical to the original image. Whatever the retrieved image is same as the original image, that is after decompression. And reversibility is necessary in most image analysis applications because suppose if you send an image, if it can, some information has been lost, definitely it will be not usable. So that is why in all the major image application areas, so reversible mechanism is popular and it is used. So the compression ratio is typically 2 to 10 times. Okay, 2 to 10 times we are going to compress the data. And examples for this reversible are Huffman coding and run length encoding. So Huffman coding, I will explain Huffman coding later. So run length coding I will explain now only. So what is run length coding? I will explain that in the next slide. So similarly, just like reversible, we have a non-reversible image compression. So that is also called as a lossy or also called as an approximation of images. So with loss of some information, ಸ್ವಲ್ಪ data ಕಡಿಮೆ ಬರುತ್ತೆ ಅಥವಾ ಸ್ವಲ್ಪ data miss ಆಗಬಹುದು. Okay, so that is why it is called as a loss of information. So lossy compression is often used in image communication. Okay, so if you want to send an image one place to another place, ಸಾಧಾರಣವಾಗಿ if the image is a very huge image, 4K resolution image, high resolution image, in those scenarios there may be some chances like this. And video, if you want to transmit a video from one place to another place, of course MP4 format, MOV format, AVI format, these are always going to consume a lot of memory. Okay, MP4 didn't already go to that. So that is a standard for format for videos. So that will consume a lot of memory. When you want to transmit the video from one place to another place, there may be chances of losing some information. And it is usually important that the image visually is still nice. Okay, even though some loss is there, the image looks like approximate, but okay, you can use that one also. The compression ratio is typically 10 to 30 times. On the other hand, if you consider reversible, it is 2 to 10 times. But in case of non-reversible, compression rate is more. Okay. So next is today's topic, that is interpixel redundancy. So this is the definition of a interpixel redundancy. Interpixel redundancy. So there is often correlation between adjacent pixels. Correlation andre ಏನಪ್ಪಾ ಅಂತಂದ್ರೆ association, relationship between the pixels. There is often a correlation between adjacent pixels. Adjacent andre neighboring pixels. So you already know about 4 neighbors. You already know about diagonal neighbors. When you combine 4 neighbors and diagonal neighbors, you are also going to get 8 neighbors. So all these type of adjacencies, we can call them as adjacent pixels. So we can predict the what we can say, the pixel value. If you consider 1 pixel, you can predict the pixel value of its neighboring or its adjacent pixel. If we can predict using a given correlation, the mechanism is nothing but an interpixel redundancy. So the value of the neighbors of an observed pixel can be predicted. It can often be predicted from the value of the observed pixel. Observed pixel means pixel under consideration. Predicted means its neighbor. Okay, we can predict the value of the neighboring pixel provided that we have a current pixel in our hand or observed pixel is there. So under this interpixel redundancy, there are two mechanisms. First one is called as that is a run length coding. Okay, run length coding is the first mechanism which comes under coding, in particularly interpixel redundancy. And second type of mechanism is difference coding. So this is also second mechanism which comes under interpixel redundancy. So ಇನ್ನೊಂದು ಬರುತ್ತೆ LZW coding or LZW encoding ಅಂತ ಕೂಡ ಬರುತ್ತೆ. So that is also I am going to explain after this session. So very important question from the perspective of examination. Okay, ಸಾಧಾರಣವಾಗಿ ಎಕ್ಸಾಮ್ ಅಲ್ಲಿ ಈ ಕ್ವೆಶ್ಚನ್ಸ್ ಸಾಧ್ಯತೆ ತುಂಬಾ ಇದೆ ನಿಮಗೆ. ಇಟ್ಸ್ ಇಂಪಾರ್ಟೆಂಟ್ ಕಾನ್ಸೆಪ್ಟ್. So try to focus, try to learn. This is very important. Okay, please be attentive. So interpixel redundancy is a mechanism through which we can predict the pixel intensity value of a neighboring pixel by using observed pixel or current pixel. Under this interpixel redundancy, there are two standard mechanisms. The first one is called as a run length coding, and second one is a difference coding. Third one kuda ide, adana LZW coding anta kuda ನಾವು ಕರೀತೀವಿ. So now we shall discuss run length coding. So what is this run length coding? Nodi, careful ಆಗಿ observe ಮಾಡಿ. Every code word is made up of a pair. ಪ್ರತಿಯೊಂದು code word ಕೂಡ it is made up of a pair. Pair ಅಂತಂದ್ರೆ ಏನು? Two values. First one is so called as a G and second one is so called as a L. What is this G? Where G is the gray level. Nodi, G ಅಂದ್ರೆ ಏನು? Gray level. L ಅಂತಂದ್ರೆ ಏನಪ್ಪ ಹಾಗಾದ್ರೆ number of pixels with the gray level. For example, ಈಗ 100 ಅಂತ ನಾವು gray level ತಗೊಂಡ್ರೆ 100 gray levels ಎಷ್ಟು ಸಲ ಇದೆ ಇಮೇಜ್ ಅಲ್ಲಿ? 2 times ಇದೆಯಾ, 3 times ಇದೆಯಾ? ಅದನ್ನೇ frequency ಅಂತ ನಾವು ಕರೆಯೋದು. Okay, so number of occurrence of this gray level in the given image, okay, that is frequency, that is represented by the variable L ಅಂತ ಕರಿತೀವಿ. ಇನ್ನೊಂದ್ಸಲ ಹೇಳ್ತೀನಿ, in run length coding we are going to represent every code word by a pair. The first variable is called as a gray level G. Second variable L is called as occurrence of that G number of times. ಈಗ 100 ಅಥವಾ 150 ಪಿಕ್ಸೆಲ್ ಎಷ್ಟು ಸಲ ಇದೆ ಇಲ್ಲಿ, ಆ ಅಕರೆನ್ಸ್ ನ ನಾವು ಇಲ್ಲಿ L ಅಂತ ಕರಿತೀವಿ. ಸೊ ನೋಡಿ, ಇನ್ನು ನಿಮಗೆ ಕರೆಕ್ಟ್ ಆಗಿ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡ್ತೀನಿ ನಾನು. ಎಕ್ಸಾಂಪಲ್ ತಗೊಳ್ಳೋಣ. ಇದೊಂದು ಇಮೇಜ್. ದಿಸ್ ಇಸ್ ದ ಇಮೇಜ್. ಯು ಕನ್ಸಿಡರ್ this is the image. 56 are the pixel intensity values of a grayscale image. So this is a grayscale image, because if you consider a color image, there are three values RGB. Since only one value is present for a pixel, means it is a grayscale image. So here, if you consider this, so the run length code for this particular image, nan mouse pointer na roll over ಮಾಡ್ತಾ ಇದೀನಿ ನೋಡಿ. ಈ ಇಮೇಜ್ ಅಲ್ಲಿ ಇರುವಂತ ರನ್ ಲೆಂತ್ ಕೋಡಿಂಗ್ ಅನ್ನ ಯಾವ ತರ ಮಾಡ್ತೀವಿ ಅಂತಂದ್ರೆ ನೋಡಿ, ಫಸ್ಟ್ ಯು ಯೂಸ್ ದ ಪಿಕ್ಸೆಲ್ ಇಟ್ಸೆಲ್ಫ್. ನೋಡಿ, ಜಿ ಅಂತಂದ್ರೆ ಏನು? ಪಿಕ್ಸೆಲ್. ನೆಕ್ಸ್ಟ್, ಹೌ ಮೆನಿ ಟೈಮ್ಸ್ 56 is repeated here? ಈ ಇಮೇಜ್ ಅಲ್ಲಿ 56 ಎಷ್ಟು ಸಲ ಇದೆ? ಫಸ್ಟ್ ರೋ ಮಾತ್ರ 3 times. So 1 2 3. So 3. Next bunny, first row only. 82 is once again the pixel, that is gray level value, and the L means 3, that is how many times 82 present in the first row? 1 2 3. So once again 3. Next, similarly 80. Okay, if you consider this 80 will be considered with respect to entire image ತಗೊಂಡ್ರೆ 1 2 3 4. Okay, next 56 again, but in terms of second row. So, okay, in terms of second row ತಗೊಂಡ್ರೆ, so 1 2 3 4 5. Okay, so this is how we can represent the run length coding for interpixel redundancy. So the code is calculated row by row. Nodi, pratiyondu ondonde row, this image represents scanning process. So first entire row will be scanned. Okay, entire row will be scanned. Then, so ಇಲ್ಲಿ ನೀವು ಹೇಳ್ಬೋದು, Okay, so ಇಲ್ಲಿ 80 ಗೆ 4 ಹೇಗೆ ಬಂತು, because this is not first row. In first row only one value is present. So ಇಲ್ಲಿ 1 ಬರಬೇಕಿತ್ತಲ್ಲ ಅಥವಾ 3 ಬರಬೇಕಿತ್ತು ಅಂತ ಹೇಳ್ಬೋದು. ನೋಡಿ ಇಲ್ಲಿ that is why there is a jump over from first to second. First ಇಂದ second row ಗೆ jump over ಇದೆ. So this is a link. ಇದು ಲಿಂಕ್, ಇದು 80 ಇಂದ 56 ಗೆ ಏನಾಗುತ್ತೆ, ಒಂದು ಲಿಂಕ್ ಇದೆ. So that is why, so the last value of the first row and the first value of the second row is always interrelated. So that is why if you consider the value 80, you have to consider this with respect to first row and as well as the second row. So that is why 80 will be taken as a 4 instead of 1 or 3. Got it? Yes? Understood?
Sir, repeat it once.
Okay, fine. So nodi illondu image ide, ಆ image intensity values ನ ಇಲ್ಲಿ ಡಿಸ್ಪ್ಲೇ ಮಾಡಿದ್ದಾರೆ. 56 56 82 82 82 83 80 80 ಅಂತ. ಈ ಇಮೇಜ್ ನ ನೋಡಿದ್ರಾ ಎಲ್ಲರೂ?
Yes sir.
ಓಕೆ, ಈಗ ನಾವೇನ್ ಮಾಡಬೇಕು, ಇದನ್ನ ರನ್ ಲೆಂತ್ ಕೋಡಿಂಗ್ ಫಾರ್ಮ್ಯಾಟ್ ಗೆ ಕನ್ವರ್ಟ್ ಮಾಡಬೇಕು. ಯಾವ ತರ ಮಾಡೋದು ಅಂತಂದ್ರೆ, ಹೌ ಟು ಕನ್ವರ್ಟ್ ದಿಸ್ ಇಮೇಜ್ ಇಂಟು ರನ್ ಲೆಂತ್ ಕೋಡಿಂಗ್ ಫಾರ್ಮ್ಯಾಟ್. ಸಿ, ಫಸ್ಟ್ ಯು ಹ್ಯಾವ್ ಟು ರೆಪ್ರೆಸೆಂಟ್, ಫಸ್ಟ್ ಕನ್ಸಿಡರ್ ಮಾಡಿ ಫಸ್ಟ್ ರೋ ಮಾತ್ರ ಕನ್ಸಿಡರ್ ಮಾಡಬೇಕು. ಸೊ ಇನ್ ಫಸ್ಟ್ ರೋ, ಬಿಕಾಸ್ ಇಟ್ ಇಸ್ ಅ ಪ್ರಾಸೆಸ್ ವಿಚ್ ಕಂಟಿನ್ಯೂಸ್ ಸ್ಕ್ಯಾನಿಂಗ್ ಬೈ ರೋ. ಸೊ ಇನ್ ಫಸ್ಟ್ ರೋ 56 is the gray level. 56 is the gray level. Next, you count the number of occurrence of 56 in the first row. How many times?
3 times.
3.
56 is present here.
3.
3 times. That is why 56 comma 3. Next, you consider 82 in the first row. How many times 82 is repeated in first row?
3 times.
3 times.
So that is why 82 comma 3. Next, you consider 83 in the first row. How many times 83 is repeated in first row?
1 time.
So that is why 83 comma 1. Next, you have to consider 80. But 80, see here, 80 is always interlinked to next row because it is the last pixel in the first row. So always last pixel in the first row and first pixel in the second row, they are always interlinked because, see here, because of this line. So that is why you compare this line with this image. So that is why 80 is, if you consider 80, you have to count the frequency with respect to first row and as well as
Second row.
second row. So what is the frequency of 80 then?
4.
1, it is here. First one, then second one, third one and fourth one. So that is why the frequency, that is the number of pixels is 4. Next, you take 56. Okay. So if you take 56, okay. So this 56 is 5 here because 1, 2, 3, 4 and 5. It is present in how many times? 5 times. It is present 5 times in the second row. But we cannot go back to the previous row because it is also the first pixel. It is also the first pixel in the second row. But we cannot go back. We can only go from top to bottom. We cannot go from bottom to top. So that is why 56 cannot be considered as 8 because it is linked to the above row. Only 5 will be considered. Got it? Got the difference?
Yes sir.
Okay. Now this is one of the very efficient coding for binary data. ನೋಡಿ, ಈಗ ನಾನು ಈ ಎಂಟೈರ್ ಇಮೇಜ್ ನ ಕಳಿಸೋದ್ರ ಬದಲು 56,3, 82,3, 83,1, 80,4, 56,5. If I am going to send this information, I can conserve a lot of bandwidth. I can preserve a lot of storage. So very efficient coding for binary data. So important to know the position and the image dimension must be stored with the coded image. The important concept is we have to identify the position, means the rows, and also the dimension, that is number of rows and number of columns, and commonly used in fax machines. This technology use ಮಾಡ್ತಾರೆ fax ಗೊತ್ತಲ್ಲ ನಿಮಗೆ, ಒಂದು document ಅನ್ನ ಒಂದು phone type instrument ಅಲ್ಲಿ ನಾವು insert ಮಾಡ್ತೀವಿ. The same document can be taken as a printout in the receiving station. Okay, fax machines ಅಲ್ಲಿ use ಮಾಡ್ತಾರೆ. So this is also another example for run length coding. Run length coding, how to represent this? Okay, so we have a matrix over here. This is the image. So this is the image, a grayscale image, and we have a table over here. The table contains the first row as a gray level and second row as a number of pixels. Now, if you consider 0, so you have to count the number of zeros here. Okay, count the number of zeros in the image, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, I think one miss the answer there. 26 zeros are present. Shall we count again? So we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay. So here, irrespective of the position, this is also possible. This is also we can use in run length coding. This is another way. Okay. Irrespective of the position of the value, we have to count it. That is, the number of occurrence of 0 is 26. Frequency of 0 pixel is 26. Similarly, we shall go for 1. So here 1, 2, 3, 4, 5. So 1 is present 5 times. Similarly, if you go for the pixel value, gray level value 2. So 2 is present here. Then again, where is 2 is present again? Here. That is 2, 3, 4, 5. Okay, so 2 is present 5 times. Next 3, 13 times. If you count the occurrence of 3, it becomes 13 times. Similarly, if you count 4, 4 is present 8 times. 5 is present here. Okay, 5 times. 5 is present 5 times. You can see here also there are 4 5s here. There may be another 5 somewhere. Okay, so like that. Okay, so the 5 is present 5 times. There is another 5. So we have, okay, here only 4 5s and another 5. Next 6 is present 2 times. So 2 times 6 is present. So this is also another example for run length coding.
Yes, sir.
So same concept will continue again. So now we can also represent in another way. There is so many different representation of run length coding. So now ಇಲ್ಲಿ ಏನಾಗ್ತದೆ, ಇದು ಒಂದು ಟೇಬಲ್. So first column indicates number of rows. Second column indicates same run length coding with respect to the gray level and number of times. So suppose if you consider the first row, ಇದು row wise ಆಗ್ತದೆ ಮತ್ತೆ. Yeah, same time. First ನಾನು ಏನು ಡಿಸ್ಕಷನ್ ಮಾಡಿದ್ನಲ್ಲ ಆ ತರ. First 0th row. 0th row ಅಲ್ಲಿ which character is present and how many times. So this is the 0th row. So here the gray level is 0 and it is present how many times? You count it. First row only. 1, 2, 3, 4, 5, 6, 7 and 8. So that is why 0, 8. So this completes first row. Now we shall go for the second row, that is 1th row. So in this 0 is present, 1 is present, 2 is present and 3 is present. So how many times 0 is present? So 2 times present. How many times 1 present? 1 is also present 2 times. Then what about 2? 2 is present only once. And 3 is how many times 3 present? How many times?
3 times.
3 times. So that is where 3, 3. Okay. So next, similarly, if you go for the third row, so these are the values. Similarly, if you go for the fourth row, so these are the values. And similarly, if you reach the 8th row, because 7 we are starting from 0 now, so that is why 7th being 8th row. So 0, comma 8. That is 8 zeros are present over there. Still you can continue. If you divide this, if you consider this is a binary, this is a decimal representation. If you convert this decimal representation into binary representation, it becomes binary length coding. Okay, like first row 0, 0, 0, 1, 1, 1. So this 0 and 8 will be taken as 1 because here 7 will be taken as the 8th row. So that is why 7 can be, if you convert 7 into binary format, what is the value? If you convert 7 into binary, what is the value? Binary conversion.
111.
111. Okay. So that is why 111. ಆಮೇಲೆ ಅದೇ ತರ ನೋಡಿ ಇಲ್ಲಿ 0 0 0 0 0 1. So 0 0 0 represents this 0. Okay. 2 means first row. So first 0, that is 1 can be represented in binary as 0 0 1. Similarly, if you consider 4 comma 2, ಈ 4 comma 2 ತಗೊಳ್ಳೋಣ. If you convert 4 into binary format, ಏನಾಗುತ್ತೆ? If you convert 4 into binary format,
0100.
100. Okay, 100 is the binary format of 4. Sari alvenappa? Yes or no? 4.
Yes.
400 is the 4. 2 entandre? 2 means it is the value, that is 1. Okay, so 1 means it is 0 0 1. Sorry, 0 1 0 0. 100 0 0 1. Here it is 100 0 0 1. Can you see the difference? Dear students?
Yes, sir.
So this is how we can also represent the run length coding in binary format also. ಈಗ ಇಷ್ಟೆಲ್ಲ ನಾವು ಮಾಡ್ತಾ ಇದೀವಲ್ಲ, ಯಾಕೆ ಮಾಡ್ತಾ ಇದೀವಿ? What is the use of this? Already ನಾನು ನಿಮಗೆ ಕ್ಲಿಯರ್ ಆಗಿ ಹೇಳ್ಬಿಟ್ಟಿದ್ದೀನಿ. I already conveyed the information. We are all doing this because in order to achieve the image compression. So how to achieve the image compression? See here. Carefully go through here. Original image requires 3 bits per pixel. ನೋಡಿ ಪ್ರತಿಯೊಂದು ಬಿಟ್ಸ್ ಅನ್ನು ಕೂಡ ನಾವು how many ಕೌಂಟ್ ಮಾಡಿದ್ವಿ, ಎಷ್ಟು ಬಿಟ್ಸ್ ಅಲ್ಲಿ ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತಾ ಇದೀವಿ? ಈಗ 0 ಇತ್ತು, 0 ನ 0 0 0 ಅಂತ 3 ಬಿಟ್ ಅಲ್ಲಿ ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡಿದ್ದೀನಿ. ಇಲ್ಲಿ 4 ಇತ್ತು, 4 ಅನ್ನ ನಾನು ಮತ್ತೆ 1 0 0 ಅಂತ 3 ಬಿಟ್ ಅಲ್ಲಿ ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡಿದ್ದೀನಿ. ಸೊ ಎವ್ರಿ ಗ್ರೇ ಸ್ಕೇಲ್ ವ್ಯಾಲ್ಯೂ ಐ ಆಮ್ ರೆಪ್ರೆಸೆಂಟಿಂಗ್ ಇನ್ ಹೌ ಮೆನಿ ಬಿಟ್ಸ್?
3 bits.
3 bits. Okay, so totally if you consider this image, what is the dimension of this image? What is the dimension of this image?
8 cross 8.
8 cross 8. ಯಾಕೆ ಅಂತಂದ್ರೆ 8 rows ಇದೆ ಮತ್ತೆ 8 columns ಇದೆ. ಸೊ ನಾನು ನಿಮಗೆ ಪ್ರೀವಿಯಸ್ ಕ್ಲಾಸ್ ಅಲ್ಲಿ ಹೇಳಿದ್ದೆ, the L average is nothing but the total number of storage required is equals to number of rows, m into n into number of bits ಅಂತ ಹೇಳಿದ್ದೆ. So m represents number of rows, 8 rows, n represents number of columns, 8 columns. So here we are using 3 bits representation. So 8 into 3, it becomes 192 bits. Okay, original image. Okay, so ಎಷ್ಟು consume ಆಗುತ್ತೆ? So if you convert that into 3 bit representation, 192 bits. Next, compressed image. Okay, compressed image has 29 runs. ನೋಡಿ ಇದನ್ನೆಲ್ಲ ಕೌಂಟ್ ಮಾಡಿ. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 so on. If you continue, you are going to get how much values here? Up to 0,8. ಎಷ್ಟು ಕೌಂಟ್ ಬರುತ್ತೆ? It is
29.
ಎಷ್ಟಪ್ಪ?
29.
29 runs ಬರುತ್ತೆ. So this is original image, this is compressed image. So 29 runs need 3 plus 3 is equals to 6 bits. Okay, ಒಂದು ಫಸ್ಟ್ 3 ಏನಕ್ಕೆ ಈ ಒಂದು ವ್ಯಾಲ್ಯೂಗೆ, ಸೆಕೆಂಡ್ 3 ಏನಕ್ಕೆ ಅಂತಂದ್ರೆ ಸೆಕೆಂಡ್ ಒನ್, ದಟ್ ಈಸ್ ದ ನಂಬರ್ ಆಫ್ ಟೈಮ್ಸ್ ಇಟ್ ಈಸ್ ರಿಪೀಟೆಡ್. ಸೊ 3 plus 3 is equals to 6 bits ಯೂಸ್ ಮಾಡ್ತೀವಿ ನಾವು. ನೋಡಿ ಇಲ್ಲಿ 0,8 ಇತ್ತು. ಸೊ 0,8 ಅನ್ನ ನಾನು 0 ನ ಈ 3, this is this 3 and 111 represents this 3. So totally 3 plus 3 is equals to 6 bits. So in total 29 into 6 ಮಾಡಿ ಎಷ್ಟು ಬರುತ್ತೆ? 29 into 6 ಎಷ್ಟಾಗುತ್ತೆ? ಕೌಂಟ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ. into 6
174.
174 in total 174 bits. ಆದ್ರೆ ಒರಿಜಿನಲ್ ಇಮೇಜ್ ಅಲ್ಲಿ ಎಷ್ಟಾಗಿತ್ತು ನಮಗೆ ಡೇಟಾ ಸೈಜ್?
192.
ಓಕೆ, ಈಗ ಕಂಪ್ರೆಸ್ ಮಾಡಿದಾಗ ಎಷ್ಟಾಯ್ತು?
174.
ಸೊ ಎಷ್ಟು ಸೇವ್ ಮಾಡಿದ್ರಿ? ಎಷ್ಟು ಬಿಟ್ಸ್ ನ ಸೇವ್ ಮಾಡಿದ್ರಿ ನೀವು? How many bits you have saved?
18.
ಓಕೆ, 18 ಬಿಟ್ಸ್ ನೀವು ಏನ್ ಮಾಡಿದ್ರಿ? ಕಮ್ಮಿ ಆಯ್ತು, ಕಂಪ್ರೆಷನ್ ಆಯ್ತು. ಇವಾಗ ನೀವು ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ವಿನ್ ಜಿಪ್, ವಿನ್ ರಾರ್ ಎಲ್ಲ ಯೂಸ್ ಮಾಡ್ತೀರಾ ಇಲ್ವಪ್ಪ? ವೈ ಯು ಆರ್ ಗೋಯಿಂಗ್ ಟು ಯೂಸ್ ವಿನ್ ಜಿಪ್, ವಿನ್ ರಾರ್, ಆರ್ಚಿವ್ಸ್ ಇನ್ ಲೈನೆಕ್ಸ್, GZ ಅಂತ ಯೂಸ್ ಮಾಡ್ತಿರಲ್ಲ, ಏನಕ್ಕೆ ಯೂಸ್ ಮಾಡ್ತೀರಾ? ಸೊ ಕಂಪ್ರೆಷನ್. ಸೊ 2.72 bits per pixel. If you divide 174 by 6 is 2.72. ಅಂದ್ರೆ ಇಷ್ಟು ಬಿಟ್ಸ್ per pixel ಇರುತ್ತೆ when you compress the image using run length coding of interpixel redundancy. ಅರ್ಥ ಆಯ್ತಾ ಇದು? ಅರ್ಥ ಆಯ್ತೇನಪ್ಪ?
Yes sir.
If you need explanation one time again, or if I have to repeat, you tell me, otherwise I will continue.
Repeat it once, sir.
Okay, fine, no problem. So ನೋಡಿ ಇಲ್ಲಿ ಏನ್ ಮಾಡ್ತಾ ಇದೀವಿ, ಪ್ರತಿಯೊಂದು ರೋ this is called as a row, this is called as a binary code. ಈಗ ನೋಡಿ ಕೇರ್ಫುಲ್ ಆಗಿ ನೋಡಿ, ಇಲ್ಲೇನಿದೆ? ಇಲ್ಲಿ ನಿಮಗೆ 0,8 ಇದೆ ಅಲ್ವೇನಪ್ಪ? ಈ 0 ನ ನೀವು ಬೈನರಿಗೆ ಕನ್ವರ್ಟ್ ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ? 0 0 0 ಆಗುತ್ತೆ. ನೆಕ್ಸ್ಟ್ 8 ಅಂತಂದ್ರೆ ಏನಪ್ಪ? 8th ರೋದು ನಂಬರ್ ಆಫ್ ಟೈಮ್ಸ್ 8 is present, and that is frequency. So but here we are taking 1 to 7 here. Okay, so that is why 8 will be taken as 7th ಅಂತ ತಗೊಂಡ್ಬಿಟ್ಟು ನಾವೇನ್ ಮಾಡ್ತೀವಿ, ಇದನ್ನ 111 ಅಂತ ಬೈನರಿ ಕೋಡ್ಗೆ ಕನ್ವರ್ಟ್ ಮಾಡ್ಕೊಂಡಿದ್ದೀವಿ. ನೆಕ್ಸ್ಟ್ ಬನ್ನಿ, ಅದೇ ತರನೇ 0,2 ಇದೆ. 0 ಮೀನ್ಸ್ ಒನ್ಸ್ ಅಗೇನ್ 0 0 0. 2 ನ ನಾನು ಫಸ್ಟ್ ರೋ ಅಂತ ನಾನು ಏನ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ? ಕನ್ಸಿಡರ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ಓಕೆ, ನೆಕ್ಸ್ಟ್ ಅದೇ ತರನೇ ಇಲ್ಲಿ ನೋಡಿ 4,2 ಇದೆ. 4 ನ ನೀವು ಬೈನರಿ ಫಾರ್ಮ್ಯಾಟ್ ಕನ್ವರ್ಟ್ ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ? 1 0 0 ಆಗುತ್ತೆ. 2 ಮೀನ್ಸ್ ಒನ್ಸ್ ಅಗೇನ್ ಫಸ್ಟ್ ರೋ ಅಂತ ತಗೊಂತೀವಿ. ಸೊ ದಟ್ ಈಸ್ ನಂಬರ್ ಆಫ್ ಅಕರೆನ್ಸ್ ನ ನಾವು ಫಸ್ಟ್ ರೋ ಅಂತ ತಗೊಂತೀನಿ. ಸೊ ದಟ್ ಈಸ್ 2 ವಿಲ್ ಬಿ ಟೇಕನ್ ಆಸ್ 0 0 1 ಅಂತ ತಗೊಂತೀನಿ. ಸೊ ಈಗ ಕಂಪ್ರೆಷನ್ ಇದನ್ನ ನಾನು ಅದೇ ತರನೇ ಎಲ್ಲಾ ತರನು ಮಾಡ್ತಾ ಹೋಗಿದ್ದೀನಿ. ಪ್ರತಿಯೊಂದು ವ್ಯಾಲ್ಯೂಗೂ ನಾನು ಬೈನರಿ ಫಾರ್ಮ್ಯಾಟ್ ಗೆ ಕನ್ವರ್ಟ್ ಮಾಡಿದ್ದೀನಿ. ನೆಕ್ಸ್ಟ್ ಕಂಪ್ರೆಷನ್ ಯಾವ ತರ ಮಾಡ್ತೀವಿ ಅಂತಂದ್ರೆ, if you consider original image, so this is the original image. So 8 rows are present, 8 columns are present. So here we are representing in ಪ್ರತಿಯೊಂದು ಗ್ರೇ ಲೆವೆಲ್ ಗೂ ನಾವು 3 ಬಿಟ್ಸ್ ಅಲ್ಲಿ ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತಾ ಇದೀವಿ. 0 ನ 0 0 0, 1 2 3. ಸೊ 4 ಅನ್ನ ನಾನು ಯಾವ ತರ ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡಿದ್ದೀನಿ? 100 ಅಂದ್ರೆ 1 2 3. ಸೊ ಪ್ರತಿಯೊಂದು ಗ್ರೇ ಲೆವೆಲ್ ಕೂಡ ನಾನು 3 ಬಿಟ್ಸ್ ಅಲ್ಲಿ ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ಓಕೆ, 3 ಬಿಟ್ಸ್ ಪರ್ ಪಿಕ್ಸೆಲ್. ಸೊ ಟೋಟಲಿ 8 rows 8 columns into 3 bits ಅಂದಾಗ ಟೋಟಲ್ ಸ್ಟೋರೇಜ್ ಎಷ್ಟು ಬೇಕು ನನಗೆ ಒರಿಜಿನಲ್ ಇಮೇಜ್ಗೆ? ಓಕೆ, ನೋ ಕಂಪ್ರೆಷನ್ ಡನ್ ನೆಟ್. ಸೊ 192 ಬಿಟ್ಸ್ ಬೇಕಾಗುತ್ತೆ. ಆದ್ರೆ ಇಫ್ ಐ ಆಮ್ ಗೋಯಿಂಗ್ ಟು ಅಪ್ಲೈ ದ ರನ್ ಲೆಂತ್ ಕೋಡಿಂಗ್ compression through interpixel redundancy. If you count this occurrence, nodi 1, 2, 3, 4, 5, ಈ ತರನೇ ಕೌಂಟ್ ಮಾಡ್ಕೊಂಡು ಹೋದ್ರೆ ಇಲ್ಲಿ ಡಾಟ್ ಡಾಟ್ ಇದೆ 4th, 5th, 6th ನಾವು ಬರೆದಿಲ್ಲ, ಅದನ್ನ ನೀವು ಅಸ್ಯೂಮ್ ಮಾಡ್ಕೋಬೇಕು. ಆ ಎಲ್ಲದನ್ನು ನೀವು ಕೌಂಟ್ ಮಾಡಿದ್ರೆ ನಮಗೆ ಬರೋದು 29 ರನ್ಸ್ ಬರುತ್ತೆ. ಸೊ ಪ್ರತಿಯೊಂದು ಕೂಡ ವ್ಯಾಲ್ಯೂಗೂ ಕೂಡ ನಾವು ಒಂದು ವ್ಯಾಲ್ಯೂ ಗ್ರೇ ಲೆವೆಲ್ಗೆ 3 ಬಿಟ್ಸ್ ಮತ್ತೆ ಅಕ್ಕರೆನ್ಸ್ಗೆ 3 ಬಿಟ್ಸ್. ಸೊ 3 + 3 that is 6 ಬಿಟ್ಸ್ ಅಂತ ನಾವು ಯೂಸ್ ಮಾಡ್ತೀವಿ. ಓಕೆ, ಸೊ 29 into 6 ಮಾಡಿದ್ರೆ ನಮಗೆ ಬರೋದು 174 ಬಿಟ್ಸ್. ಬಟ್ ಆಕ್ಚುಯಲ್ ಇಮೇಜ್ ಕನ್ಸ್ಯೂಮ್ ಆಗಿರೋದು 192 ಬಿಟ್ಸ್. ನಾವು ಕಂಪ್ರೆಸ್ ಮಾಡಿದಾಗ ನಮಗೆ ಬಂದಿರೋದು ಎಷ್ಟು? 174 ಬಿಟ್ಸ್. ಮೀನ್ಸ್ 18 ಬಿಟ್ಸ್ ನಾವು ಏನ್ ಮಾಡಿದ್ವಿ? ಸೇವ್ ಮಾಡಿದ್ವಿ, ಪ್ರಿಸರ್ವ್ ಮಾಡಿದ್ವಿ. ಸೊ ದಟ್ ಈಸ್ ನಥಿಂಗ್ ಬಟ್ ಕಂಪ್ರೆಷನ್. ಕಂಪ್ರೆಷನ್ ಮೀನ್ಸ್ ರೆಡ್ಯೂಸಿಂಗ್ ದ ಫೈಲ್ ಸೈಜ್. Okay, and if you divide 174 by 6, 2.72 bits per pixel we are going to get. So this is the run length coding mechanism, how it works. Artha aita? Shall we proceed?
Yes, sir.
Now, so this is all about run length coding. Next one is a difference coding anta barta. Yenappa idu difference coding? The name itself tells everything. Difference andre ಫಸ್ಟ್ ವ್ಯಾಲ್ಯೂಗೂ ಸೆಕೆಂಡ್ ವ್ಯಾಲ್ಯೂಗೂ ಡಿಫರೆನ್ಸ್ ಮಾಡ್ತೀವಿ. ನೋಡಿ ಯಾವ ತರ ಫಾರ್ಮುಲಾ ರೆಪ್ರೆಸೆಂಟೇಷನ್ ಇದೆ ಅಂದ್ರೆ ಎಫ್ ಆಫ್ xi is equals to xi ಅಂದ್ರೆ ಒರಿಜಿನಲ್ ವ್ಯಾಲ್ಯೂ ಹಾಗೇನೆ ಇರುತ್ತೆ. ಯಾವಾಗ ಅಂದ್ರೆ if i is equals to 0. If i is equals to 0, we are going to keep the value as it is. Suppose if i is greater than 0 ಅಂದ್ರೆ ಫಸ್ಟ್ ರೋ ಬಿಟ್ಟು ಸೆಕೆಂಡ್ ರೋ ಏನಾರ ನೀವು ನೆಕ್ಸ್ಟ್ ವ್ಯಾಲ್ಯೂ ಏನಾರ ಹೋಗ್ತಾ ಹೋದಂಗೆ ಫಸ್ಟ್ ವ್ಯಾಲ್ಯೂ ಮಾತ್ರ ಆಸ್ ಇಟ್ ಈಸ್ ಇರುತ್ತೆ. Next value, if you go, it is nothing but difference of first value and second value. Bari formula ಹೇಳಿದ್ರೆ you can't understand properly. We will take an example here. So this is the image. On the original image ಇದೆ ನನ್ನ ಹತ್ರ 56, 56, 82, 82, 82, 83, 80, 80, 80, 80. So this is the image. If you apply the difference coding on this image, how compression can be done? See here, this is a code word. So code of f of x comma y. This is f of x comma y. You are applying this formula, difference coding on this image. Nodi 56. 56 is the first value. That is if i is equals to 0. So this is i. I is equals to 0 here. So we have to keep the value 56 as it is. As it is. Sarina? Sarina, since I is equals to 0, this is I is equals to 0, this is I is equals to 1, this is I is equals to 2, so on up to, okay? I is equals to 0 irodrinda, xi na hage itkondidini, that is 56 will be taken as it is. Sarina?
Yes, sir.
Next banni ivaga second value, second 56. Now I is equals to 1 ivaga I 1 agutte, means I is greater than 0 because 1 is greater than 0. So xi minus 1 andre 56 minus its previous value, that is 56 minus 56 is to
0.
So that is why 0 will be taken here. Next banni matte 56. Here I becomes 2, 2 greater than 0. So 56 minus its previous value. 56 minus 56 again
0.
0. Next we have encountered 82. That is 4th position and 4 is greater than 0. So 82 minus its previous pixel. That is 82 minus 56. That is
26.
26. Now we shall go for 82. The previous value is 82 because I is 5 here greater than 0. 82 minus 82 is again
0.
0. Next 82 minus 82 again 0. Now 83. I is equals to 7. Okay. I is equals to 7. Since 7 is greater than 0. 83 minus 82. What is the value?
1.
1. Now I is equals to 8. Once again greater than 0. So 80 minus 83.
Minus 3.
Similarly 80 minus 80.
0.
80 minus 80.
0.
80 minus 80, 0. So this code is once again calculated row. This is row by row. Okay, once again first row. Next we shall go for the second row. this process will continue. So both run length coding and difference coding are reversible and can be combined with Huffman coding. So iveredu kuda reversible antandre original image nanu as it is we can get without loss, okay, lossless. So we can also use this in Huffman coding next ಹೇಳ್ಕೊಡ್ತೀನಿ. Okay, ಈಗ difference coding ಅರ್ಥ ಆಯ್ತೇನಪ್ಪ?
Yes, sir.
Okay.
Yes, sir.
So this is an example for difference coding again. So this is the original image. This is a difference image. See here, 9 will be taken as it is 9. Whereas this is 8. It is because I is 1 here. That is 8 minus 9. That is minus 1. 7 minus 8 is minus 1. 7 minus 7 is 0. 7 minus 7 is 0. Next 5 minus 7 is minus 2. 5 minus 5 is 0 and 0. ಅರ್ಥ ಆಗ್ತಿದೆಯಾ ಇದು ಡಿಫರೆನ್ಸ್ ಇಮೇಜ್ ಯಾವ ತರ ಬರ್ತಾ ಇದೆ ಅಂತ?
Yes, sir.
So next is LZW coding. That is what I am telling you. So this is another type of coding called as a LZW. ನಿಮಗೆ ಶಾರ್ಟ್ ನೋಟ್ಸ್ ಅಲ್ಲೆಲ್ಲ ಕೇಳಬಹುದು ಎಕ್ಸಾಮ್ ಅಲ್ಲಿ. So what is LZW coding means? It requires no prior knowledge. ಅಂದ್ರೆ ನಮಗೆ earlier knowledge in ಬೇಡ. Okay. So only pixel probability distribution values, based on that we are going to do this. So how this will work? Assign fixed length code words to variable length sequence. ಒಂದು ಫಿಕ್ಸ್ಡ್ ಲೆಂತ್ ಕೋಡ್ ಅನ್ನು ನಾವು ಅಸೈನ್ ಮಾಡ್ತೀವಿ ಯಾವುದಕ್ಕೆಪ್ಪ ಅಂದ್ರೆ ಸೀಕ್ವೆನ್ಸಸ್ ಆಫ್ ವರ್ಡ್ಸ್ ಗೆ. ಸೊ ಇಟ್ ಹ್ಯಾಸ್ ಬೀನ್ ಪೇಟೆಂಟೆಡ್. ಇದು ಆಲ್ರೆಡಿ ಪೇಟೆಂಟ್ ಆಗಿದೆ. ಸೊ ಇನ್ US, okay, this is a number, patent number. So this can be used in GIF images, TIFF images and PDF also. PDF file formats ಅಲ್ಲಿ LZW coding ಅನ್ನ ಅಪ್ಲೈ ಮಾಡ್ತೀವಿ. So this is an example over here. So example ಅಲ್ಲಿ ಏನಾಗ್ತದೆ? So we have an image over here. Okay, 39, 39, 126, 126, so on up to that. So as the encoder examines the image pixels, gray level sequences, that is blocks that are not in the dictionary, are assigned to a new entry. ಅಂದ್ರೆ ಈ ವ್ಯಾಲ್ಯೂಸ್ ಬಿಟ್ಬಿಟ್ಟು ಹೊಸ ವ್ಯಾಲ್ಯೂ ಯಾವ್ದಾರ ಬಂತು ಅಂತಂದ್ರೆ we are going to assign a new value for this. For example, ನೋಡಿ 0, if you consider is 39 in the dictionary. ನೋಡಿ 39, whether it is there in the image. 39 is there in the image, so it will be not added to the it is there in the dictionary. Okay, 39 is already there, it is there in the image, so it is not added. Next, what about 39 minus 39? Because difference coding ಮಾಡಿದಾಗ ಏನಾಗುತ್ತೆ, 39 minus 39 ಏನಾಗುತ್ತೆ? So 0 is not present in the image. 0 is not at all present. Okay, so that is why it is not present in the dictionary antivi. So that is why this 0, that is 259, 0 has to be added to the dictionary, and then add 39 minus 39 in entry 256. This is 0, 1 up to 255 because 256 gray levels are present. So this new value is not present, that is 39 minus 39. So this will be added to the 256th position. Okay. Similarly, if there is any new type of values, we are going to add to the dictionary. So bari ನಾನು ಈ ತರ ಥಿಯರಿ ಹೇಳಿದ್ರೆ ನಿಮಗೆ ಗೊತ್ತಾಗೋದಿಲ್ಲ. I am going to do a problem on this LZW coding ಮೇಲೆ ಒಂದು ಪ್ರಾಬ್ಲಮ್ ಸಾಲ್ವ್ ಮಾಡೋಣ. ಅವಾಗ ನಿಮಗೆ LZW coding ಕ್ಲಿಯರ್ ಆಗುತ್ತೆ. ಓಕೆ, ಸದ್ಯಕ್ಕೆ ಎಷ್ಟು ತಿಳ್ಕೊಳ್ಳಿ. ಐ ವಿಲ್ ಇನ್ನೂ ನಿಮಗೆ ಡೀಟೇಲ್ ಆಗಿ ಹೇಳ್ತೀನಿ ನಾನು LZW coding ಅನ್ನ. So differential pulse coding or modulation coding is another type of coding here. So it is also called as a predictive coding. Prediction ಅಥವಾ guess ಅಂತ ಕರಿತೀವಿ ನಾವು. Each pixel value is predicted based on the neighbors, just like interpixel redundancy itself is a prediction. So that is why differential pulse code modulation, EPCM, is also one of the technique which is used in interpixel redundancy. But ಇಲ್ಲಿ exam ಅಲ್ಲಿ ಅಂತ ನಿಮಗೆ ಕೇಳಿದ್ರೆ ನೀವು ಬರಿಬೇಕಾಗಿರೋದು run length coding, difference coding, if possible LZW coding ಬರೀರಿ. ಬಟ್ ಇದು ನಿಮಗೆ ಬಿಡ್ತೀನಿ ಚಾಯ್ಸ್. DPCM either you can write or you can leave. Okay. So the difference between original and predicted image is differential or residual image. Means the difference between the original and the decompressed image is give the difference or residual image. That is a much less dynamic range of pixel values. ಒಂದೊಂದ್ಸಲ ಏನಾಗುತ್ತೆ, ನೀವು ಡಿಕಂಪ್ರೆಸ್ ಮಾಡಿದಾಗ ನಿಮಗೆ ಕ್ಲಾರಿಟಿ ಕಡಿಮೆ ಆಗ್ಬೋದು, ಕಾಂಟ್ರಾಸ್ಟ್ ಕಡಿಮೆ ಆಗ್ಬೋದು. ದಟ್ ಈಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಎ ಲ್ಯಾಕ್ ಆಫ್ ಡೈನಾಮಿಕ್ ರೇಂಜ್ ಅಂತ ಕೂಡ ನಾವು ಕರಿತೀವಿ. So we have made a lot of discussions on histogram processing in our previous class. in image segmentation allu kuda nanu idan ಬಗ್ಗೆ ನಿಮಗೆ ಹೇಳಿದ್ದೆ dynamic range about thresholding anta. So that is what. So the differential image is encoded using Huffman coding. Okay, so Huffman coding I will explain that later. So this is all about the references. I have collected something. So shall we discuss a problem on LZW coding, or if it's enough, I will stop here. Dear students, shall we continue? Shall we solve a problem, or shall we stop here? Have you understood this? Any doubts? Okay, we'll stop here. We'll try to solve the problem of LZW in the next class. Okay? Shall we stop here, dear students?
Yes, sir.
Okay, I request all of you to give the attendance in the chat box. So thank you so much, dear students, for joining image processing class. Have a nice day.